So we saw in the last lecture that some functions are equal to a power series on part of their domain. So for example, 1 over 1 minus x equals the sum from 0 to infinity of x to the n for all values of x between minus 1 and 1, and the natural log of 1 plus x is the sum of the alternating series, the sum from 0 to infinity of minus 1 to the n x to the n plus 1 over n plus 1 for values of x between minus 1 and 1. And likewise we had a power series which coincided with the values of tan inverse of x on the interval from minus 1 to 1. In this section we're going to develop a method to find power series expansions or representations for a wider range of functions, and we'll also devise a method to identify the values of x for which the functions equal this power series expansion. And this isn't always going to be the entire interval of convergence of the power series, nor is it going to be the domain of the function. So let's make precise what we mean by saying that f of x has a power series expansion at a point A. This means that there's some open interval around A extending from a minus r to a plus r, so that for all values of x in that interval, f of x equals the sum of a power series centered at A. In other words, the sum from 0 to infinity of Cn x minus a to the n, where the Cn's are constant. And notice that if I take a equals 0, saying f of x has a power series expansion at 0 is the same as saying that f of x equals the sum from 0 to infinity of Cn x to the n for all values of x between minus r and r for some r greater than 0. Last day we concluded that 1 over 1 minus x, the natural log of 1 plus x, and tan inverse of x all had power series expansions at 0. Now sometimes a function has a power series expansion at a point A and sometimes it does not. One of the benefits of the existence of such an expansion is that we can approximate values of the function with a polynomial. And another is that we can actually sum some series that we could otherwise not sum. So we have two main questions here that we're going to answer. Question one is, if a function f of x has a power series expansion at A, can we tell what that power series expansion is? And secondly, for which values of x do the values of f of x and the sum of the power series expansion coincide? And we'll see that in answer to question 1, we can give a very precise formula for the power series expansion of A if it exists. And for question 2, we'll look at how to create some bounds on the error in estimation by partial sums of the power series, and this will help us answer question 2.